Hello, I'm Megan Beckley, Program Director for the Electrical and Computer Engineering Department Heads Association and moderator for this webinar, Teaching in Our Virtual World, brought to you by Intel. Before introducing our speakers, I have a couple housekeeping announcements. We will be accepting questions throughout the presentation and ask that you submit all questions through the chat feature. Additionally, the webinar will be made available for on-demand viewing this week, along with the presentation slides. Now it's my pleasure to introduce our speakers, Larry Landis, Dr. Lowe, and Tyler Sheaves. Larry has 35 years experience in a wide variety of functions in the electronics industry, including managing the IC development team that designed the first Apple iPod SoC, marketing, sales, and project management for numerous ASIC and FPGA products. His current role is running academic outreach for the Intel FPGA division. Dr. Jan Lowe is a professor of the Department of Electrical and Computer Engineering at the University of Massachusetts Lowell. His research interest spans broadly computer architecture and network systems, and his current research focuses on heterogeneous architecture and systems, software-defined networking, and deep learning. Finally, Tyler Sheaves is an intern with the university program at Intel's Programmable Solutions Group. He is an incoming electrical and computer engineering PhD student at UC Davis, where he will research integrated circuit hardware and IP security. With that, I will hand it off to Larry to get us started.
Great, thank you. Go ahead and share. Is that showing up?
Looks good, Larry.
Looks good. All right, let's see, full screen, that should. All right, well, thanks everyone. Let's see if that will. Not sure how to make you guys disappear. Let's see. Are you guys seeing this panel of your picture, or are you seeing my entire PowerPoint?
We're seeing the full PowerPoint.
You're seeing the full, okay, so maybe that's something. All right, so go back. Just a quick introduction. Again, my name is Larry Landis. I am with Intel, and I run the FPGA university program over here in San Jose, California. And in a typical year, this year I had 4 international trips and probably about a dozen domestic trips. So in a typical year prior to COVID, I traveled around a lot, visiting university, going to conferences, had all intentions of going to ECE in Orlando, but things changed quite rapidly, starting actually around January, because I was slated to travel to Malaysia then, but we just had a last minute to cancel that, and probably a good idea. And so my focus has changed a lot this year to enhance and help out in online training. So my talk today is showing you different online resources to learn about FPGAs for both undergraduate students and graduate level students. So just if you sort of look at a typical industry academic program, and obviously we have a very healthy one here at Intel. We have a number of different functions. We want students graduating knowing about FPGAs, preferably Intel FPGAs, but if they use our competitors' FPGAs, that's always a good thing as well. And we want universities to know about our latest generation products. We want students trained so we can hire great students such as Tyler, who will present in a moment. And lots of students around the world are learning about Intel FPGAs every semester. And then we have many research engagements on Intel FPGAs and a wide range of Intel products. So a little bit of background on our FPGA University program. This was launched in 2006 when we were Altera. In 2015, we were acquired by Intel, and the program continues on. This was launched by a Professor Stephen Brown, who is a prof over at the University of Toronto, where him and some colleagues started creating materials specifically targeted at universities to learn about digital logic and computer organization, embedded systems, and now we also have graduate level training as well. A former University of Toronto grad student by the name of Sean Pang started a company called Terasic that's based in Taiwan. Now there are over 100 employees, and they build FPGA-based boards specifically for education, and they have a wide range of boards that they sell at very reasonable prices and really rich feature sets for academia. And we offer a web page with lots of different coursework, a means to acquire boards and licenses, and so on and so forth. So just really, I spent a lot of time talking to professors daily, and you guys are amazing because this transition going from in-person to remote training in a week, I know is really stressful, a really tall order, and you have a deep responsibility to keep students engaged and educated and generate the next generation of students to solve really hard problems, including curing COVID. Hopefully this thing is behind us at some point. Feels like a little bit of a ways away, but we'll get there. The good news is, as tech folks, we're just kind of familiar with rapid pace of change. So adopting to using all these online tools is, just like we go through Moore's law and we adapt to new products all the time. This rapid pace of change is something that is in your blood. So again, thanks for the hard work and training our students. I feel really good about where things are heading for the fall. Probably not as chaotic as it was in the spring. So if you sort of look what happened over a course of a week, you sort of took this system of teaching students that is primarily in person for literally, thousands and thousands of years, where people are gathering in classrooms. And as industry folks, I run a lot of in-person workshops that are, a day or so as opposed to semester long, all to this online environment. And so what we're going to discuss today is the offerings that we have, so that you have a set of resources that you can use for FPGAs in the classroom. So we'll start with the undergrad work. The coursework that we offer on the left is digital logic / digital systems type coursework. Then we have coursework on computer organization, where you're studying things like instruction sets on various CPUs and all of the inner workings of a microcontroller or microprocessor. And then the final set of coursework for undergrad would be embedded systems, which is primarily about embedded computing running a Linux operating system, how device drivers work, and how an SoC can interact with an FPGA on our SoC FPGA product lines. And then on the right side, we have a list of typical graduate level courses. Dr. Lowe will talk about his work with heterogeneous computing, using a number of C++ derivative languages. OpenCL is one that's been out there in the marketplace for a while, and Intel is very much involved in a initiative called One API that uses DP C++ or Data Parallel C++ to describe digital electronics. And then there's lots of different graduate work on networking, security, so on and so forth. And we offer material for all of this. So for FPGA development, if you've done any work with FPGAs, there is a suite of tools that does all sorts of different things to compile your design, close timing, describe different things, debug, so on and so forth. And suite of tools is called Quartus. It's been in the marketplace for decades. And the good news is it's free for the low-cost families, which are very popular in the undergraduate program. So you download the tools, you don't need any licensing. We also have an agreement with Mentor to distribute their model sim simulator. And we also have a version of Eclipse for this processor we call the NEOS processor, which is about 20 years old now with a number of different revisions. This is a so-called soft processor, meaning it's built out of the FPGA lookup tables, and it's great for education for putting together different types of embedded systems. And so just a little bit more on NEOS. The instruction set looks quite a bit like the MIPS instruction set, but it's specifically geared for embedding into an FPGA for sort of control, status, kind of system management. A lot of people use it for power management, bring up, and things like that. It's not like a full-blown application processor necessarily. If you're going to do something with a Linux operating system, you'd probably want to utilize our ARM-based product lines with our SoC products. But the NEOS is great for setting up different types of projects for students where they can have a processor and FPGA working in conjunction to solve problems. These NEOS processors, they run in the range anywhere from about 2,000 lookup tables to about 10,000. So they fit easily in any of our FPGA families, and we have lots of IP that you can connect together. We offer a set of tutorials on how to use the Quartus tools and NEOS. So we offer these in both Verilog and VHDL versions. And after the webinar, you will receive a PDF file that has this information and all of the, if you hover over any of the underlying areas, everything is a clickable link. So you can just go through and explore the different offerings of tutorials. So these are great for handing out to students where they can learn how to use the Quartus software on their own, and you can go in and integrate those into your classroom quite easily. They're used by, I think we're up to about getting close to 2,000 labs that are being run around the world using these tools. Okay, so these are just different tutorials we offer, and on a variety of topics that you can go off and explore. And then when you look at the coursework, here is a set of 12 labs that would easily fill up a semester of digital logic training, where in the tutorials, the students learn how to run the tools. And then in the labs, the students give a particular problem set that is to design something interesting in digital electronics, such as the labs that you see here on a variety of increasingly more complex projects. So again, lots of universities use this material. You just go to our website and you can download the material. If you want the source for it, we can get that to you in LaTeX format. Also, if you want the solutions, you can request the solutions and we'll send those out. To send out solutions, you need to be a verified faculty, so we don't have students that are plagiarizing the materials. When you sign up for that, you just send a picture of your faculty ID, and then you'll be eligible to get the solution manuals for the material as well. So that's digital logic for computer organization. This is primarily about the operation of a microcontroller slash CPU. They're offered in either the ARM A9 instruction set or our NEOS soft processor. And here you can see a number of different labs that we offer. We also have a very simplified IDE we call the monitor program that's used in conjunction with this coursework. Much easier to use than, say, a Visual Studio or a Eclipse or other IDEs. So it's a good starting point for students to learn about instruction sets and step through their code. And then finally, the coursework for embedded systems is shown here. This is all about using embedded Linux to show you how you would use an SoC FPGA device. We start off with learning about Linux, then we talk about drivers, and then there's various applications where you interface with FPGA logic and go across different bridging functions and bridging logic, where you can go in and read the memory map of different devices that you can connect up sensors and accelerators and things of that nature. Just a little bit of background on the Terasic products. So they sell these for a number of years, and here's just an example of some different boards. Some of the nice things about these boards is they're nice and compact. The price is very competitive. Lots of different features that are typically used in a digital logic or digital systems type of class. You can look at the $55 board. The D10 Lite has lots of switches, LEDs, 7-segment displays, VGA. It also has an Arduino header, and so on and so forth. And then each of the boards have, different features suited for different type of learning environments. Things like audio control, a more expansion capability, and so on and so forth. So go ahead and take a look at Terasic's site. These are available for purchase. There's special academic pricing that you can get, and also there's donations. So when you go to our university site, you can sign up as a member and request donations of a few boards for samples. If you like what you see, you can request more boards to fulfill a classroom, or we might have situations where we look at your request and we split. We'll donate some and you'll purchase some. So every case is kind of different depending on our budget and what it is that you're requesting. But go ahead and explore to the Terasic site. They have a really rich offering of dozens of boards. They also have things like robot kits and higher end accelerator boards and so on and so forth. So again, a great partner for us, very good quality products that are quite popular. They've sold over 100,000 of these boards to the academic community. The next topic I'm going to talk about is hands-free remote labs. This is something that came up quite quickly in the when COVID came online. So Tyler and I have been working on this, and he'll give a quick demo in a moment. But the idea behind this is you're used to having students come in and share boards in your electronics lab, and now the students are off campus, and it might be difficult to get each student a board. You might not have the budget for it. There's expenses involved and so on and so forth. So what we did is we came up with an idea where the board sort of looks like a video game, and it looks quite cool. I think you'll enjoy it once you see the demo. What we have is a means to access the boards where you do need to make some changes to your lab, but it's fairly minimal. So if you have a lab manual that is using an Intel FPGA board, you can adapt it to this hands-free environment quite easily with just probably about 1-page addition to your lab manual to explain to the students how they would be able to operate these hands-free. And what you do here is you take boards that you have, either you're already running Intel or you acquire Intel boards, you connect them to a server at your university. We have some profs just hosting it at home. So they just go off and get a server at home, connect it up onto the internet, broadcast the IP address, and students can go off and address the boards. And it supports multiple OSs. And this GitHub link at the bottom, you just click there and all the information to run this is available. So general idea is you have students that are learning from home, and they can run the tools either on their own PC, or they can, if depending on the university setup, they can also run it, the tools on a server provided by the university. We also have something called DevCloud we'll talk about that we're populating with boards as well. So that might be another possibility for students where they can do the compute on the Intel cloud services. So we connect up multiple of these DE10 Lite or any, we're going to have other boards as well. It's anything that has a USB connected board can be connected up through a USB hub, and the students can go off and run their lab material. So with that, I'm going to stop sharing for just a moment, and Tyler, our UC Davis PhD intern, will share his screen and show you how it works.
Thanks, Larry. Let me share here. All right, so as Larry said, this is something that's kind of meant to complement like an existing lab manual. It was built kind of in mind that most professors aren't going to rewrite all of their material to accommodate a new system. So this program that's running here is Quartus. It's the software that's used to program Intel FPGAs. And there's a hierarchical description of our design, and it starts at the top level here. And you can get a view of all the files by pressing this files icon in the project navigator, and we can see the three source files for our project. Going to top here, there's two primary things that need to happen at the top level to accommodate using this GUI. One is the user obviously needs to place their design at the top level. And that would be standard in making test benches or other things that are common in logic design or any project that included an FPGA. Now, additionally, students would need to interconnect their design with this pin IP, which is a platform designer IP that we've created that allows you to interface and communicate with a remote board. So once the design is implemented at the top level, then you can start up the GUI. Now, this design in particular is called Night Rider, which includes a scanning LED and a reset that is capable with the flick of a switch or the push of a push button. There's several ways to reset the design. So this would be typically what a student would fill out as part of their assignment. And then once interconnected and instantiated with this top level, they could simply compile by pressing play. Now, I've already compiled it to save time, and I'll launch the GUI. But if the way we've written this is that once they compile, the GUI will automatically launch afterwards. They don't need to worry about any commands or scripting or anything. So let me launch the GUI here. So as Larry showed earlier, this is the DE10 Lite board. It's $55. And right now, I have several boards sitting at a remote location with Quartus running on it. And my setup is I have a Mac computer with a virtual machine that I've set up as something called a JTAG server, which is a software that allows you to host multiple boards on a single machine and then communicate with them remotely. So in this scenario, I'm a client, aka a student, or even a professor trying out this. And if I go to board select here, I can see a list of all the boards that are available on my JTAG server. I can select one. And right now it's performing a program of the board. It gives you some prompts. There's more coming, and we're also going to add ways to change the JTAG server credentials and passwords so that you can have more flexibility there. Once this design's linked now I'm seeing effectively what a student would see right after they program this design. So you'll see that this LED is scanning erratically left to right. It's too fast for us to perceive. So I'm going to slow down the speed that it scans at with another feature that we have called a parameter, which is a 32-bit adjustable register that I can click here, type in a hex value. It's a great way to teach number systems, etc. So I'm going to type in 19, hex 19 here. And we can see that we've divided down the speed of the scan slow enough so hopefully you can see it over the web. So you can interact with the board by pressing push buttons or flicking switches. You can see in this case that the push buttons and switch 0 here all correspond to a reset operation. So I'll speed it up here. You can see that the scan speed increases. So that's all I have for this presentation now. What we're working on in the future with this particular project is we're going to scale up to multiple users concurrently trying to program, and we're going to make this a more robust tool. But at this point, it's a great way to host your boards, and then students can remotely log in. It's great, especially if students are international or they don't have access to these boards. Thank you.
Great, thanks, Tyler. Back to sharing. Okay, hopefully you're seeing that again. So that's a demonstration of our hands-free remote labs, and we think this is a great resource for professors to utilize in the coming semester. It's a means where, especially if you have multiple sessions of a lab where you have, maybe a few labs being run per day and you don't have enough boards to get out to each student, you can go off and utilize this environment, have the students go in and connect your, build sort of a dev kit farm at your site, or perhaps a prof could set it up in their office at home, which is, we see a few instances of that going on to try to work around some of the challenges of teaching during these tough times with COVID. Other things that we offer as services to universities, perhaps I've been, or other colleagues from Intel have been at your university's site to run hands-on workshops, and generally these can be anywhere from an hour to 4 hours. Here's some of the courses that we offer, and we are happy to work with your university if you want to educate your students on a specific topic about Intel FPGAs. The first 4 on the list are ones that are recorded and are entirely self-guided, but I would be happy as well to offer this as a instructor-led class. We could use it in conjunction with the remote lab environment that we just demonstrated, and give your students some new skills on FPGAs through various workshops. We also have just a wide variety of training on all sorts of online or what we call virtual training. So online is entirely self-guided, where you watch a video. In some cases, there's an included lab, and you go off and do your coursework. In other cases, there are fairly complex topics that are done virtually, where students log in and get access to the equipment needed to run the lab. If you're a professor and share your professor credentials, you can go off and take any of the training that's offered on our FPGA technical training site. And again, when you get the PDF file, just go ahead and hover over this, and you'll get the URL to all of the training. So please just distribute the PDF file to your colleagues so that they can see all of this material that we offer. So again, these are just some helpful links to get access to the coursework, to the boards, to the GitHub site, and so on. Just follow there's just many links, dozens and dozens of links in this PDF file of resources that you can utilize for training your students. Now let's move over to the grad level side of things. So we're going to concentrate on a couple of cloud services. Across Intel, there's probably a dozen or more different cloud services that we access, but The FPGA Dev Cloud and one we call a HARP are one specific to FPGA education. So in general, there's a lot of interest and work in academia, particularly at the grad and research level, on using a processor in conjunction with an FPGA to solve a particular workload. We offer FPGA acceleration cards. We call them PAC cards, or platform accelerator cards, that connect up through a PCI Express connector up to a Xeon processor, and support lots of DDR memory, or we also have our Optane memory that are populated on different types of boards. So this is a very high level of interest in the research and grad community to utilize these type of boards. And really the challenge in using these in education is because of their expense, very difficult to get one student per board. It really wouldn't be economical to do that. So about a year and a half ago, we started up what we call Dev Cloud. And prior to that, we had something which we call HARP. This is the Heterogeneous Hardware Acceleration Research Program. That is sort of a research-centric cloud service that we offer. So we'll describe in a moment which service you might use depending on sort of your usage model, whether it's teaching or research. But these are great resources for you to utilize and learn more about FPGA acceleration. So the HARP, let's start with that. That was our original cloud service. This is, again, the Hardware Accelerator Research Program. Around 2014 or 15, we had a combo chip where we put a Xeon and an FPGA in a single package that we offered on HARP, and then we expanded it to these PAC cards. And what they do is they host long-term research engagements. These are invited research. So if you're interested, there's an email address that's included in the PDF. You can contact the folks that run this program and describe what sort of research that you do. You get, in some cases, you get access to grant money and to subject matter experts to help you out. You need to reach out to that program and inquire on what they can do to use the HARP program. On the right side is the Dev Cloud, and the Intel FPGA Dev Cloud is a series of high-speed servers running 20 nanometer and 14 nanometer FPGA cards, and you can run a variety of workloads for teaching and short-term development projects geared for grad students. So if you look at the Dev Cloud environment, it really ranges from RTL-based design flows where it's for the hardware-centric EE type folks that that have spent maybe a year or two writing Verilog, VHDL system Verilog, and describing what we call an AFU, which is an accelerator functional unit, to be running inside an FPGA. So the working model for many of these type of acceleration functions is we describe all of the I/O, the Ethernet, the DDR memory, and so on and so forth around the perimeter of the chip. And then the designer goes off and puts in a workload, whether that be packet processing or vision processing or so on and so forth. And then you use OpenCL, RTL, HLS, these different languages to get workloads running on a combination of a CPU and an FPGA. Most of the descriptions beyond RTL are based on higher level languages that are derived from C++ with different extensions to describe the parallelism available to you in FPGAs and in other types of semiconductor technology. a brief overview of the cards that are inside the Dev Cloud and also in the HARP cloud. This is showing our 20 nanometer product, and this has 1.15 million lookup tables, lots of memory, and so on and so forth. And then we have a 14 nanometer card as well. And probably getting into early next year, we'll also offer our 10 nanometer Agilex cards up into the FPGA Dev Cloud. So to summarize, if you look at the overall curriculum that you might find in a typical electrical engineering or computer engineering type of program, at the undergrad level, it's typically digital logic, digital systems type of courses, computer organization, embedded systems. There might be some other electives that show up with robotics and other topics that involve FPGAs. And then when you get into the grad level, it tends to be a lot of interest currently in heterogeneous computing, which is using a CPU plus an FPGA to solve a specific workload that might be running either in an edge type of environment or a cloud type of environment. So learning hasn't stopped. I'm actually really impressed how well students are doing. I think it'll only get better in the fall as we're sort of adapting to this unusual world that we're living in. Hopefully things start looking more normal, perhaps in the spring and fall. It feels like most people are online, but we'll just have to see. We know it's been a big strain for profs. I speak to profs daily on what they're doing for lesson planning in the fall, and again, go through the PDF file, look at some of the resources that we have to help you out so that you can get your students trained, educated, employed at companies like Intel and other folks to solve these difficult problems that we have. We need a pool of amazing engineers and scientists to get us to solving some of these extraordinary problems and challenges that we see in front of us. So thanks, and I am going to hand it over to Dr. Lowe, who we speak weekly. So Dr. Lowe and I have been working together on the Dev Cloud, and he's been using OpenCL in his training for many months, and I'm honored to have him take over and show you some of the work that he's been doing. Thanks.
Thank you, Larry, for the introduction. Can you see my screen?
Yes.
All right, so so I'm going to talk about my experience teaching a few computer engineering courses at UMass Lowell during this unprecedented difficult times for everybody. My name is Yan Luo. I'm a professor at the Department of Electrical and Computer Engineering, and I have been with the department for a while, and currently my research is focused on several areas: heterogeneous computing, software-defined networking, and machine learning and deep learning. And the courses I taught here had many different flavors, but recent years I taught Microprocessors 1, which is a junior level course focused on assembly language programming and computer systems. And another course is Microprocessor 2 in embedded systems. That's a continuation of Microprocessor 1 and an introduction to embedded systems. And in the past spring and summer this year, I taught heterogeneous computing. And also in the past, I taught software-defined networking. Today, I'm going to talk about heterogeneous computing, what I did with this course in the past spring and summer, and also my plan for Microprocessor 2 embedded systems for the fall semester. A brief introduction of the heterogeneous computing course. This course focused on heterogeneous computing architecture, as Larry mentioned, CPU plus FPGA or GPU, And also it teaches data parallel programming using languages like OpenCL and DPC++. The way I design this course is I make it as FPGA centric. I know that OpenCL can support other process architectures like GPUs, but for the purpose of our curriculum, this course is now FPGA centric. And this course is a tech elective for undergrad and graduate students in our degree programs. Also, it can be used as a technical elective to our FPGA certificate program. We typically offer this course in the spring semester, and also in the summer, I offered it as an online course. Besides those lecture materials, I added hands-on practice components for this course. Currently, the course has 4 labs, 3 focused on OpenCL programming, and the last one is the data parallel C++ or DPC++. And these lab assignments require FPGA hardware, or at least some of them require FPGA hardware for experiments, and some of them we're doing in emulation mode, as I will explain a little bit. So I want to just describe what the changes I have made in the 2020 year. In the past offerings of this course, I used a Intel Stratix 5 development board with OpenCL SDK, and I had my TA installed on the hardware and the software SDK Linux server. And also, in the past, students use VPN to access the board. And so once they get on the university VPN, they need to use their own login credentials to log in to this particular Linux server. And they have to timeshare the access, because we cannot afford people compiling or even loading the binary to the FPGA card at the same time. In the spring and the summer of this year, the changes including we, instead of using our own single board FPGA on the server, we used Intel Dev Cloud. And Dev Cloud, as Larry mentioned, that it's an online resource provided by Intel that has a pool of FPGA cards and also compute servers. And compared to the last year, when we use the Intel FPGA Dev Cloud, we don't need any VPN access. And students will apply free account that will allow them to log into Dev Cloud. Also, the plus side is that they can access the card, any card, any compute servers at any time. And compared to the past offerings, because the new One API and the DPC++ framework was just released this year, so I'm fortunate to get the early training materials, and so I can add a few new lectures and lab materials on One API and a DPC++. Also, these changes allow me to move the course from a traditional face-to-face course to a fully online course in the summer. Here are some of the lab assignments I gave out for the summer 2020. Basically, we have 4 labs, and some of them are based on OpenCL, talking about data partition, data parallel algorithms, and how to design OpenCL kernels. And also, we have a lab to use Leibniz formula to calculate pi. In that lab, students are learning MapReduce methods and memory barriers and data parallel programming. Those 2 labs are run on Dev Cloud, but we do not require the students to run the real FPGA cards. They can do emulation. For the 3rd lab, students are required to build a board test program, which will do performance profiling using OpenCL events. And for this lab, they are required to generate the binary and load it into the FPGA cards. And the last lab is a matrix multiplication, as we did in the first lab, but this time they're required to use this new data parallel language, DPC++. So here they will learn One API, the n-dimensional programming, the data partition, and DPC++ kernel simulation, and data parallel programming. And all the lab materials I have open on GitHub. You can follow that link. So talking about the benefits that DevCloud bring to us for remote teaching and learning, I have to mention that all the changes I made, was before January, and who knows that this huge COVID thing came upon us in an unprecedented way. So fortunately for us, for me, and also for the students, Intel DevCloud did bring immediate benefits. We do not have to have staff and TA on site to support the system deployment, maintenance, and also it gives us the access to the latest and very, very diverse FPGA hardware and development tools available on DevCloud. And DevCloud is a cloud environment, so it has basically 24/7 availability to the students. Also, from my perspective, I see we can have long-term benefits. It greatly improved the productivity. So there's a lot of support packages and tools, scripts provided by the Intel FPGA DevCloud team that will allow the students to sign up and access and run the code very quickly. It flattened the learning curve of new technologies, for example, OneAPI, DPC++, high-level synthesis, all the tools available on the DevCloud. It lowers the barrier for innovation. Here, I just talk about the teaching part. We do use DevCloud for our research projects as well. Okay, so as we're planning for the next semester, I'm assigned to teach this Microprocessor 2 Introduction to Embedded System course. So when I plan my lectures and lab, I have several things considered, just to cope with unprecedented COVID pandemic. I guess most of the universities like us, we do not have a full back to campus plan. So there are a lot of courses that will be delivered virtually, and the same case for my course. So what I consider to be beneficial for students and for me is to have a set of tools that can be readily available and be cost effective. So for my course, I plan to have the students own their own lab kit, in particular this Arduino kit, which is available on Amazon. And this is an Arduino-based dev board with a variety of sensors and actuators included in this kit, and it's very cost effective. And for this embedded course, students will do a lot of lab assignments, and they, in a typical setting, they will need to access oscilloscope, logic analyzer, and power supplies in the lab. But now we don't have the full access coming in the near future. So fortunately, they have this lab in a box, and this is a device that we show a picture here. We have different versions of it, from analog devices or digital. It's basically a USB-based device. They can use it as a oscilloscope or logic analyzer or even a power supply. So they can build their lab assignments, their design, and using these tools, try to troubleshoot or debug or analyze. So this will allow them to do lab anywhere at any time. And for us, it eliminates the shipping and all these logistics. We have to, if we have to provide them the lab materials, we have to ship to them. In this case, they can just buy their own kit. To compensate the cost, I choose to use free resources. For example, there's free textbook. It's a very good book from Professor Lee and Xixia from Berkeley on the cyber-physical system design and / embedded system design. So this is my plan for the fall 20. And this is just a plan, and we will anticipate additional changes as we go. But I just throw this pointer here to encourage people to think about how they're going to plan for the upcoming semester and academic year. And that's all I will need to say for now. Thank you.
Thanks. Appreciate discussion, Dr. Lowe. Good material. Okay, so I think we're going to take the last couple of minutes to go through some of the questions that have come up. I'll go ahead and share the screen. Let's see here. So feel free to type in the screen. Let's see. Okay, so the first question was, what boards do you recommend for a digital logic course or a microprocessors course? So for the digital logic course, I'd recommend the DE10 Lite board. I think my video is still on. Can someone just verify that you're still seeing me?
Yes.
Okay, good. So this is the DE10 Lite board, $55 for academia and for both faculty and for students. They just need to register with a student ID, and they can get the student price of $55 from Teresic. You can also buy these on Amazon for, I don't know, I think they're $90 or $95 for the board, and it'll show up the next day if Amazon Prime. Some of the features that it has, if you can kind of see the lights blinking, there's an accelerometer function in here, a 50,000 lookup table device, which can hold a Neos processor and quite a bit of compute on here. And then you can also see the Arduino header. So if you wanted to buy different Arduino plug-in boards, if you want to get, say, a Bluetooth radio or Wi-Fi, you could interface there. We've done some fun stuff with NeoPixels. If you're familiar with those are like strings of LEDs that are individually addressable. So lots of coursework you can do with that. Then it also, you're asking about a microprocessor course. So we have a number of boards that are SoC FPGA type boards. There's one that's called a DE10 Nano. That's about $100 or $110. There's a DE1 SoC that has a lot more interfaces that runs $175. Comes with an SD card, and you can just connect it to through HDMI or VGA, depending on the board, and it'll be running embedded Linux. And you can go off and learn how to write kernel modules and also interface with the FPGA side. So let's say you wanted to put a bunch of sensors connected to that board. You could use that for a microprocessors course. Of course, Dr. Lowe talked about kind of an embedded course using Arduinos. They're great, easy to learn environment, tons of material out there. So they're all good stuff. The next question from Dr. Osius: is Quartus compatible with Mac? Unfortunately not. It runs on Windows and it runs on Linux, but we have lots of people setting up virtual machines to run from the Mac and connecting to a virtual Windows machine. Slides and presentation material recording will be available, and I think that was already answered. There's a question about, can multiple students log in to one board at the same time? So in the virtual environment that we discussed and Tyler demonstrated, it is a single student per board. Although there is a feature in there where the professor can set a timeout period. So if, let's say you have a student, they're doing a project, typical type of project might be write code, simulate it, and then finally test it out on a board. So they really don't need to occupy the board for that long of a period. They need to prove it out. They could be one of these students that's too anxious to they skip simulation, go straight to the board. That's possible as well. But you can set up a timeout period where they can only access it for, say, 5 minutes, and then it'll time out, and then another student can use. And we're looking at different mechanisms to support, lots of users that could get a pretty good sized lab going without people waiting too long. So the timeout is just one of many features that we're thinking about to you know, help in this online remote hands-free environment that we're putting together. Let's see, M2K and digital and ADT may not be available. What do you do? Honestly, I'm not on the analog devices and digital devices. I can't really speak. That's a Dr. Lowe question, I suppose. Not sure how to answer that. Let me jump to the next one, and then we can return to that. You used DE0 Nano for my digital logic course. Can they be used in ways you described? If not, what resources are available? So we're adding boards as we go along. We started off with this DE10 Lite board, and we're putting instructions together that a professor can actually add their own board. But we're also going to put together a library of boards that you can access. So depending on what features a DE0 Nano should be okay, we do need to look at things like if there is a console interface and there's a USB to UART interface. We'll come up with solutions so that we light up more of the interfaces than just GPIO. That's what we have going right now. But we're starting to think through how to connect to a UART, how to connect to the VGA so that you can utilize many different features on this board. So if I missed any questions, let me know. This is the ones I'm seeing so far in the chat window.
So Larry, let me jump in on about the logic analyzer little kit, USB kit.
Sure.
So Professor Raffler asked about the cost about that board. You know, I think we had our students, the freshman students, buy that board, that little kit, in their first year, and they will use that for a number of years throughout the curriculum. So that's how we justify on the cost side. So at this time, when I teach the senior and junior level courses, they already have it. So that's why it's not going to be additional cost for them to take my course. Hope that answers your question.
Okay, good. Next question from Dr. Hafeda. Is the JTAG server plug and play, and is it supported by Intel? So the JTAG server is part of the Quartus package, and if you are running a server that's connecting to one or several boards, you just load the JTAG server software up there. It's easy to configure. When you load it, the device drivers should just come up and work. If not, it's very easy to load the device drivers and be up and running. Basically, the circuitry that's going on, if you can see this board, is I have a USB connection here. I have an FPGA in the middle, and there is a small device. There's actually two devices. There's a USB, what we call an FTDI chip, that is sort of the interface to the USB, and then there's a small FPGA that does bridging between the USB and JTAG. So that circuitry is all included. There's no special cabling. This is just a standard USB. I think it's a type A type connector that's included with the board. Next question is, hi, I would like to have access to the lab solution for the different courses. I've already sent an email, but I did not receive any answer. That's a problem. We will, if that isn't giving you results, at the end of the slide set that you receive, there's two contacts, myself and Terry Barrett, my colleague, who can field your question about getting you access to the lab solutions. We definitely like to help you out. There's a question about real-time digital signal processing or control. In terms of coursework, we actually, the best way probably to go about that is to go to MATLAB and look at what they have. We have a product that we call DSP Builder, which is a interface between MATLAB and mapping that into RTL and then compiled down to an FPGA. So I would use the MATLAB training, and then there's some tutorial information on how to use DSP Builder. that'll take your MATLAB description, map it to the DSP functions within the FPGA, and then you can run your experiment, you know, on a hardware accelerator. Let's see, problems running USB Blaster with Win 10 in recent years. Any comments on that, or where can find solutions? Google seems to similar problems. There is a Intel forum that you can Google and find. There's a section on university and FPGAs. That is a moderated place. And we have our application engineers are monitoring that for questions, and that should be the location that you go to find out more information about having problems with the USB Blaster. So I would go to the Intel forum. And I think that's it for questions. And wow, we're right. Okay, 1 minute past the hour. But thanks everyone for your time and attentiveness. Hopefully we've given you some ideas on ways to help you in your upcoming semester. I know many of you are going to be running your coursework online. And if there's other ways that we can help out, please contact us and let us know what Intel can do to facilitate your training with FPGAs.
All right, well, it looks like it's time to wrap up this webinar. Thanks to Larry, Dr. Lowe, and Tyler, and thanks everyone for joining us. On behalf of ECETA, I'd like to thank Intel for making this ECE webinar possible. Please visit the ECETA website at eceta.org to access the on-demand version of this webinar and other ECE webinars from ECETA. Thanks again and have a great day.
Thank you, everyone.
Thanks all. Have a great fall semester.